The next idea from section 5.5 is the remainder in alternating series. So essentially what we can do is we can actually approximate so many terms to as much accuracy as we want. That's what's kind of neat about this theorem. And it's really simple to do. Essentially, all we have to do is pay attention to this inequality here. All we have to do is pick the n plus 1 term, and our remainder is going to be within that, whatever we want it to be. We're going to work a problem out in just a second here. So let's take a look at this problem. Okay, this is from the book, problem number 303 in section 5.5. So this says, how many terms in cosine of theta equaling this thing here are needed to approximate cosine of 1, accurate to an error of at most 0.00001. All right, so what we're going to do is we're just going to take a look at this problem here. But first, there's some issues that we got to take care of. So the first thing to realize is, how do I take this? Oops, excuse me. How do I take this here? And turn it into a series. That's the first thing. Because notice this, I'm going to want to start at 1, and that's just because I want to. I can start at 0, I can start at other numbers if I want to, but it's going to change my b sub n and my -1 thing. So the first thing I'm going to address is that -1 thing. So if you notice here, the first term is positive. So what that tells me then is that this is going to have to be an even power. So I'm just going to do this, n plus 1, because when I plug in a 1 there, that's going to make that a 2. So -1 squared is going to be +1. So that's that piece. Now the other piece is a little more interesting and strange at the same time. Because when I look at the top piece here, and I look at just this exponent, that exponent, if you look at that sequence of the exponents, they're even. So I know right away that on the top, it's going to be some form of 2n. Now what I have to consider here is, I need that first term to be 1. So that tells me then, if I'm looking at my 2n here, I'm going to need that to be a 1 at first. So what that means then is, if I put a minus 2 here, then when I plug in a 1 here for that first term, that's going to actually be 2 minus 2, which is 0. So anything to the 0 power is 1. So that actually works out pretty good. And then for the bottom, I do a similar thing, and actually kind of the same idea. Now, one thing I have to understand about the bottom is, when I plug in a 1 here, look what I get. That's really going to be a 2 times a 1 minus 2, so that's going to be a 0. And a lot of times when people look at zeros, they say, oh, zeros are undefined when they're on the bottom. But this actually turns out to be 0 factorial. And actually 0 factorial equals 1. So for that one, that would be okay. So just something to think about as we're going through it. Okay, so that actually works for this series that we see here. It actually equals this series here. So they're the same. Okay, now from here, what we're going to do, once we develop that, is we're going to talk about the cosine of 1. Now, the cosine of 1 implies that our theta is going to equal 1. So then, for our series, n equals 1 to infinity, the -1, n plus 1, what we're really dealing with here is really 1 to the 2n minus 2 over 2n minus 2 factorial. Okay, so this is what we're going to look at now. So now if you look back at the formula here, let's take a look at this. It says what we have to do is we have to take the bn plus 1 term. So that's what we're going to do now. So we're going to go back to that. And now we're going to take our bn plus 1. So bn plus 1 is actually going to equal 1 to the 2n plus 1 minus 2 over 2n plus 1 minus 2 factorial. And when we actually simplify that, I'm going to end up getting a 1 to the 2n over 2. Oops, let me keep the same variables here. Over 2n factorial. So that's actually what we end up with for our bn. Okay. And since we're really only talking about finite terms here, we can really just call this 1 over 2 to the n factorial. So now what we're going to do is just take a look back over here. And now we're looking at this Rn here, which is right here. So if we look at what we have, ours has to be greater than this here. And that really is just equal to 1 over 100 million. So all we have to do here is just take that 1 over 2 to the n factorial and say, hey, that has to be less than or equal to 1 over 100 million. And this is just using that theorem. So this here is our Rn, and this is what we need to be less than here. Okay. So now in doing so, I can say that by flipping the denominators, I can say that this is really just saying 2n factorial is greater than or equal to 100,000. And essentially at this step, I'm just going to try numbers. So for instance, if I put a 3 in there, so if I take this factorial here, and that's going to be 2 to the 3, that's really 6 factorial. And right away I see that that's 720. So then I say if I do a 4, let's try a 4, so that's going to be an 8 factorial. And an 8 factorial is 40320. So then I plug in a 5 for n. So again, that's my n, remember that. So when I plug in a 5 there, that's really, I'm really looking at 10 factorial. And 10 factorial is 362,880, which is still, which is bigger than 100,000. So that's where we stop. Don't have to go any further than that because look at, I was looking where 2n factorial had to be bigger than 100,000, but I wanted the smallest n and where that actually happened at. So then when I look at where I went up here, when I plugged the 2 n's in, this here was 40,000. And then this here jumped way over 100,000. So that tells me then that this number here, where n, where n equals 5, is going to be where our answer is. So we know that n equals 5. So now if we write this all out, all we have to do is go back here. And then if I have this sum here, n equals 1 to 5 of negative 1, n plus 1. And this being 1 to the 2n minus 2 over 2n minus 2 factorial, that this number here would actually be that value. That would be as close up to those that number of decimal places. Now, check this out. I actually punched this in my calculator for both the 5 and the other number, and look at what happens here. We can clearly see that, hey, the 5 decimal places, 1, 2, 3, 4, 5, are all accurate the same, and then that 6 decimal place is where it actually changes. So that just checks.